Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. One of the most demanding technological challenges in space exploration is the development of materials that will withstand the rigors of launch, orbit, and re-entry. This requires the expertise of exceptional scientists and engineers. One such engineer is Gerald Blackburn, who has directed the development of materials, processes, and spacecraft production, and have met those scientific and technological challenges. Ladies and gentlemen, Jerry Blackburn.
Good morning, ladies and gentlemen. Thank you so much, Cindy. I really appreciate that remarkable introduction. It's the second remarkable introduction I had. The first one I would like to share with you was one given many years ago by my son in his school classroom on career day. I had been invited to speak to the class, and the teacher asked my son, "Stephen, please introduce your father." Well, Stephen was a shy little boy, but he shuffled up to the front of the class, and he turned and he looked at me as I walked up, and he says, "I want to introduce my father. He works at the Spaceship factory." Many years later, I realized that was the finest introduction I have ever had. And I do, and I did. I work at the Spaceship factory. The image you see here on the screen is one that you never forget. It's a matter of perspective, they say. Many of you may have had the opportunity to go to the California Science Center and see our endeavor. And you get a similar view of what is referred to sometimes, and we used to lovingly call it the belly of the beast. It's a remarkable machine. It's a very powerful image, and especially when you stop and think that what you're also looking at are thousands and thousands of stories about how it was created, how it got there. I'm going to share one of those stories with you today. It's based on an article I wrote a couple years ago called "The Glass Spaceship." When I would talk with student groups, the questions always came up. "Mr. Blackburn, what'd you make the spaceship out of? What material do you use?" We used a lot of materials, 2,500 different materials as a matter of fact. But the most predominant material was glass. So hence, the glass spaceship. Sir Isaac Newton has a famous quote, "If I have seen the future and further, it's because I stand on the shoulders of giants." I too was able to stand on the shoulders of giants, beginning with my father. After he passed away, going through many of the images that he left behind, I came across this one which just overwhelmed me, even to this day. The war broke out, and like many of the young men in the country, he volunteered and duty called. Reported to San Diego. My mother, his beloved at the time, recently married, because he was shipping out, took this photo of him standing on a pier down in Long Beach or San Diego, looking out to the South Pacific. And I look at that and I wonder what was going through that young man's mind. Just married, his wife pregnant with me, This is truly the greatest generation. And the giants whose shoulder we stand on are the greatest generation. People ask, well, how did we do things like Apollo and the shuttle and all of that? This is how we did it, because we had the greatest generation's shoulders to stand on. They were the ones that took us to the moon and to space. I had the benefit of that experience for almost 50 years now, an aerospace career. Yes, I know, I was very young. As a matter of fact, I was only 17 years old when I started working for North American Aviation, right across there in El Segundo. A couple of projects over there that were calling for help. X-15 was finishing up. They had a new program called the XB-70. Let's go build a machine that'll fly at Mach 3. Okay, yeah, let's go do that. So I got to work on that for a while. But as I learned early on in the aerospace business, count your blessings while you've got them, because it changes tomorrow. And it did. XB-70 was canceled, and I called my new wife, who was pregnant with my daughter, and I said, honey, I've got good news and bad news. The bad news first, I just got laid off at North American. Oh my God, not to worry. I just got hired over at Downey at Space and Informations Division. I'm going to work on the Apollo and the Saturn II. So, packed up, moved down south a little while, and spent the next 40 years there working these programs. It's been a tremendous career for two reasons for me. One, I never had to take any of my experience or skills and work on a weapons system. I always worked on exploration. And people would ask, you know, all that money we spent, all that time going to the moon and everything, what do we get? Is it worth it? Yes, it's worth it. For me, it's worth it. I was able to raise a family, learn things about materials and spacecraft and aerospace I never would have learned before. Go to the moon, go to space, to the space station, put my kids through school. Yes, it was worth it. And I'm one of 500,000 other people who can make the same kind of statement. So yes, it was worth it. One of the things that was very unique about this time was when we got the Apollo contract and then later the shuttle, there were no recipes or instructions or cookbooks of how to go do that. How do you go put 3 men on the moon and bring them back safely and, oh, by the way, do it in 10 years? How do you do that? Well, I guess we got to go figure it out. And that's what we engineers do. Engineers ask questions. It's about asking questions. It's what I tell young people and students today. Learn how to ask the questions that you need to find the answers to. It also helps as an engineer if you love problem solving. Oh yes, my wife would constantly remind me, you're always looking for another problem to solve. Yeah, that's what I do, pretty much. That's what I've learned. One of the other major benefits from these programs like Apollo and Shuttle was learning how to be part of a team and work as a team. Going to the moon, building shuttles, well, that was good. That was a product and a takeaway. But learning how to communicate, learning how to work with others. The young students, when I talk to them, they'll say, Mr. Blackburn, did you ever go to the moon? No, but I helped make the machines that got there. And yes, I did go to the moon in a way, my own vicarious way. But you know, I learned something once again. No one person can do it alone. We have to do it together. We live in a community right here. We're all very benefit from this Southern California community because this was the home of so many of the magnificent men and women and their flying machines. Aviation, so much aviation that was done right here. Just one curious fact that you may or may not know. We were doing some research and came across a photo. Did you know that the first fueling of an aircraft happened right here in Long Beach at the harbor? We have a picture of it. Two men, a pilot and a co-pilot. And the co-pilot gets out on the wing with a 5-gallon jerry can and walks across the wing and pours the gas into the other airplane. Beautiful. Boy, that's a comment about the people back then. The other one is a beautiful little story about a young lady named Netta Snook. Snooky, they called her. I love her name. Snooky learned to fly in the Midwest, came to California like everyone who learned to fly. And she had a guy by the name of Glenn Curtis teach her how to fly. And then she needed a job, so she went over to Downey, to the Kenner Airfield at the time, talks to Bert Kenner and said, I understand you have another airfield you're opening up over in Southgate. Yeah. She said, need some help? He says, yeah. He says, how'd you like to be the airport manager? The first woman municipal airport manager in these United States, right there in the Southgate. She gets a hold of Bert and she says, can I give flying lessons? Sure, go ahead, Snooky. Have you got any students? Yeah, I got this young girl who wants me to teach her to fly. Her name's Amelia Earhart. Another story for another time. Rockets, spaceships to the moon, Space Shuttle, all of this right here in our backyard. Ed Smith, chief engineer on the shuttle program, who I'm still working with, by the way, on a task force, keeps reminding us and me, he says, Jerry, you remember that shuttle when we built it. It's a truck. NASA wanted a truck. They didn't want command modules that splashed down and threw away. They wanted a truck to go back and forth to take stuff up. And that's what we designed, and that's what we built. Last month, Deborah shared with you some wonderful, wonderful stories and information about extreme engineering that they had to do for the Webb telescope. Another magnificent story that is still unfolding. Yeah, we know about extreme engineering. We had to design and build a vehicle that would take astronauts and cargo to orbit, do it efficiently, easily, and over again. They wanted cargo. Oh, well, you've got to up the cargo capacity. Apollo could take 3 astronauts and a few pounds of stuff, souvenirs and whatnot. We want 65,000 pounds in that bird. And this was the real key that we struggled with. Okay, what kind of warranty do you want on it, NASA? Well, we want 10 years or 100 missions. That was the warranty that we had to work to. We would design it for a minimum of 10 years and 100 missions. We'll revisit that in a little while. Oh, and we would love to get the cost per payload down. Cost per payload on Apollo and other vehicles at that time, $10,000 a pound. That would never fly, as the pun goes. We need to get it down to something more reasonable. We'll try. Oh, and then build us a fleet. We want a fleet of 5 of these things. Okay, we'll go do that. So the designers, NASA, our engineers, started looking at how are we going to do this? Because the considerations in a design of a spacecraft like this, first you've got the structure. Structure's got weight conditions, strength conditions, life, remember 10 years, 100 missions, maintainability. You got to be able to service it and maintain it. You don't want to keep changing it out. You don't want to keep adding a booster every time you fly it, although that did do that. Then there's the environmental control considerations. Oh, environmental control. Yeah, because we're here on this Earth in this environment, but we're going up there with a totally different environment. So we got to monitor that. Well, the instruments that monitor this environment are not the same as the ones that monitor that environment. Oh, don't forget, we got a crew on board, and they don't do too well breathing in vacuums and cold space, so give them, and the astronauts came back and made it very clear, we want a shirt sleeve environment. We don't want these big bulky suits. Oh, and again, don't forget, service life, keep that in mind. Well, one of the things about Shuttle that I'm really proud that we did, unfortunately it was at the cost of 3 very good men on Apollo 1. We learned a serious lesson. Safety and reliability was the #1 factor in all design, in all production on the Space Shuttle orbiter. And of course, reusability. We actually had a visit from Pan American Airlines. You remember the old Pan American Airlines. Well, NASA said, we want to keep flying these things and we might want to go commercial with a commercial orbiter someday. Oh my. Well, how would you maintain and do a turnaround and all that? So we invited Pan Am to come in and sit with our designers and pick our brains and let us pick their brains. What would it look like? I have a great graphic. I should have thrown it in here, but if you remember Pan Am, they had a PR promo with an airline and this little bird sitting on the back with a cigar. Pan Am, the only way to fly. Well, we had our PR guys doctor up a shuttle orbiter with that image in it. Needless to say, that got put on the back burner for a while. And then we get to the reality, and this is where we're headed. Build it. Design it, build it. It's one thing to dream it, draw it, now build it. And I can't tell you the number of times that the designer would come back screaming, the manufacturing engineer threw our drawings back. They want us to revise them because they said they can't build it that way. Okay. It began the dialogue of integration, of having designers and manufacturing people work together, side by side. So, keeping all these things in mind, simple. Go build us a space shuttle. The number one environmental issue that we had to tackle and consume most of our time was re-entry heating. Now, you're all familiar with re-entry heating, believe it or not. Has anyone ever seen a shooting star in the night sky? I know today it's hard to even see a night sky, but in the days we had a night sky, and occasionally when we have our meteor showers, you can see them. Material coming back into the atmosphere, trying to enter, igniting and burning up. It's an effect. It's an effect of the speed of the mass of the material coming through the upper atmosphere, interacting with the air molecules there. For a long time, it was discussed and presented to the public as, well, do you want to know what it's about? It's about the friction of the spacecraft coming through the air. Well, that's not quite right. It's actually a different physics phenomenon, thermodynamic problem called adiabatic pressure. A vehicle coming through, like you see here with the Apollo, it is coming through and it's got a surface area, and as it's coming through so fast, it's compressing the air. And as air compresses, it heats up. That's where the heat comes from, not the friction. So once we look and we understand, and we learned a lot of lessons from previous spacecraft like Gemini and Mercury, and X-15 taught us a lot about re-entry. That was one of the reasons we built the X-15, was to test that. And we learned that this thermal heating had to be managed. We needed to manage it in some way. And you really only get two choices. One is what we called ablative, and that's what we used on Apollo. So as the vehicle came through, the heat shield of Apollo would heat up. And as it would heat up, it would burn, it would melt, and it would flow off. It would flow off into space. That's what happens to the meteors and so forth. And that's okay because it's taking the heat away from the structure of the spacecraft. So ablative works. However, when you've used it all up, you're in trouble. So you've got to really manage then the aerodynamics of how you fly that spacecraft and re-enter it, the angles of attack and all of that sort of thing. But there was another method, and it was an absorption method where, okay, the heat comes in and it gathers. Well, let's just store it for a while. Let's have a material that will absorb that heat just long enough to get through the atmosphere and then re-radiate it back out into the lower atmosphere. That turned out to be our solution for Orbiter. Now, well, okay, we've got a method and we think we got a process. Gee, have we got a material? We need to go invent a material. Well, we had to invent a lot of materials. The thermal protection system on the orbiter is a long list of materials. I'm only going to talk about one of them today. I'm going to talk about what you see, the HRSI, the black tile. This is an HRSI tile from the orbiter. I'll put it up here on the table later so you can explore some of these materials. But the first thing you'll notice about it is it's very light. Hardly any weight to it at all. It feels strange too. Yeah, it feels kind of like an egg. It's got a glass-fired coating on it. It's got a softer core, but one of the properties of it is this will absorb the reentry heat that is exposed to the spacecraft, the plasma as we call it. It will soak into this and soak in it like a sponge, and it keeps it there. There's one of the demonstrations that we do, which I don't do, I used to, but I could take this and I would take a blowtorch and I would heat this to white hot heat, 5,000 degrees. And then I would pick it up with my fingers. How do you do that? You're gonna burn yourself. No, you're not. Because as soon as I touch it, the heat dissipates away. It's that magic. This was a magic solution. Lockheed developed it. We figured out how to get it onto the orbiter, and that's where the first real question and problem came in. It's kind of like, and to give you some way of thinking about this, let me suggest that I want you to take your car and I want you to cover every surface of that car with raw eggs. Okay? That's our problem. Cover it with raw eggs. How do you do that? Well, first of all, wow, I got to get a lot of eggs. Then you got to figure the eggs are kind of round, so how are you going to attach them? You got to attach a round egg to a flat surface. Well, we've got flat tiles going on to a round surface, a curved surface, but you got to attach them in some way. Oh, and then I want you to drive it from here to Vegas. Oh, you didn't say anything about that. Yeah. All right, so you get the picture. It's a real challenge. There's a lot of things in the air here that's being juggled. And we took each one of them, as I said before, asking the questions that had to be asked, and then figuring out what the answer to that question was. But you know what? Every time we figured it out, there'd be another dozen questions we'd have to ask. But we got there. And we did figure it out. We figured out that the way it works is you have to put a material between the tile and the surface of the orbiter that absorbs movement. It's called SIP, a strain isolator pad. And once again, it's a common material that you know today as Nomex. Now, Nomex is a felt. You can buy it on Amazon. And it's the same material that's used in fireman suits, in race car driver suits, because it's got another great property. Besides being flexible and easy to work with, it's got a high temperature. It's good to 500 degrees. So you can see we're starting to build our solution here. So at a point in time, we said, look, we're there. We know what we're going to do, and this is it. But we had to cover different areas of the vehicle for different temperature zones. The gray that you see in this image here, which is on the leading edges of the wing and the nose cap, those are the highest temperature areas. Those get up to 5,000 degrees on reentry. And we had a special material called RCC, reinforced carbon-carbon. Think of it as diamond before diamond, but it would absorb and it could handle that reentry. But once again, it had another quality that we had to watch. It was very brittle and very susceptible to damage and impact. Up on the sides and the top of the wings and so forth, temperatures weren't as high because the belly of the beast was taking all of that heat. We put some very thin tiles there for a while on the first mission called LRSI. But it was too flexible and they damaged too easy. So one of our engineers came in one day, said, one of our fabricators in the shop thinks they've got a different solution. We were using a fabric, a quartz fabric, for the inside of the payload bay. And this young lady said, you know, I make quilts. I can quilt this and make a blanket that could go on these curved surfaces. Good. That's what we're going to do. And AFRISI was born. AFRISI, flexible reusable surface insulation. All right. So we're getting there. We pretty much got this figured out. We've got tile, we've got blankets, we glue them onto the vehicle. Hey, we're good to go. Palmdale, 1978. We're getting ready to ship Columbia, first vehicle, first flight, STS-1 down to the Cape. There's 30,000 of these tiles that have to be on that orbiter. And we're at the point where NASA's chomping at us. They want that vehicle delivered. Our management's putting the pressure on. Get that thing out of the hangar. Let's get it done. We have 7,800 more tiles before we can ship it. No, you're going to ship it now. There's a condition in business and in manufacturing that they call ship short. You may have heard the term. Ship short, it means I haven't got all of the stuff here, but I got enough that I'm going to send it to you so you can at least have it, part of it in your hands. So we were going to make arrangements to ship short Columbia down to Kennedy Space Center. Here's where my story for today begins. My boss at the time, a good man that some of you may remember, Jorge Diaz, incredible engineer. Jorge had been up at Palmdale overseeing some of the installations that were tagging up, and he comes into the labs down in Downey, and he walks in, and we're sitting there, and George is white. George doesn't normally look white like that. He says, we said, what's wrong, George? He says, we got a problem. He said, NASA was up in Palmdale pressing us to get that vehicle shipped, and one of the NASA guys reached up to the belly and touched one of the tiles, and it came off in his hand. OMG. Oh my God. What is that about? Well, the first reaction was, doesn't he know you're not supposed to touch those tiles without gloves on? Not the problem. So George told us, he says, look guys, he says, you have 72 hours. I'll be back, and this was on a Friday, so guess what we're doing for the weekend? He says, I'll be back on Monday. I want a test method for testing every single tile that's installed on that vehicle, and a new method for installation that's going to ensure that tiles aren't going to come off. I tell you, that was a weekend from hell is the term they used to say. But we did it. We came up with a very unique testing device. But now we've still got the problem. This vehicle's got to ship. We got all those holes that have to be filled. They literally went out to the shop, took foam blocks, cut simulated tiles, put them in there and duct taped them in. We're going to fly that thing down on the 747. We're going to get it down there and put it in the OPF. And we're going to finish the testing of the tiles and the installation of those other 7,800, plus any remove and replace that we may have to do. Holy, how long is that going to take? We don't know. But you're not going to come home until it gets done. We had a crew of 400 engineers and technicians that went down there for 2 years, training personnel, working in a building that was not designed for manufacturing and testing. Talk about a problem to be solved. It was the nightmare of all nightmares. The OPF down in Florida it's just built for turnaround, for servicing fluids and putting instruments in and that sort of thing. It's not made for production, let alone testing and all of that. We had to do a back shop to actually produce the tiles that needed to be replaced. Every single tile on that orbiter has a unique part number and drawing. So there's 30,000 drawings. Not only that, but our testing device was a unique thing called the spider. You had a tile that was in the middle of the array, as we would call it, and you had to put a proof load on it. So we had to make a device that acted as a vacuum chuck that would pull a load on the tile without tearing the face of it out. And it had to be pulled in exactly the right way. So imagine this tile glued to the surface. It's glued to the surface, and you got a device that's going to pull it straight up. Well, that means we need to know a math calculation called the centroid. What is the center of this tile? Where is it? Mark it, because the chuck that pulled it had to be located right over that. Back at my office in Downey here, I also had the group that handled a lot of the drawings, and I said, I need a crew. I need a crew that knows math, that can calculate the centroids of irregular shapes, because all the tiles aren't shaped square. They are all different configurations and geometries. We had to put together a training program to teach people how to do math geometry. You get the picture. Well, we had a Tiger team. George led the Tiger team, George Diaz and myself, as part of the Downey contingent. And since George was senior, he got the first shift, I got the night shift. But it was 24/7. And we're working with people 3,000 miles away from our home office and facilities. We learned a lot. We learned so much I can't even begin to tell you about things other than just the engineering. That ship short, we did solve the problem. We tested them all. We got the job done. 610 days later, we had all of the tiles installed, we had all of the tiles tested, and we certified that vehicle for flight. Let's go. It's a go launch, for launch. So, we had a successful launch with one little hitch. Some of our TPS engineers, they said, we know this is going to work, but we're putting a special team together. They're called the Bucket Brigade. On the bottom of the orbiter launch pad, there's this huge flame bucket where the flames from the solid rocket boosters and the engines blast into. And it's deluged with water and so forth. It takes quite a while, several hours, for that to cool down before anybody can go near it. But our guy said, we've got a team of about 15 people, the bucket brigade. They're going to go down into the bucket to count the number of tiles that are in the bottom of the bucket. Oh, yeah. The gentleman who was the engineer was in charge of that, a personal friend of mine. I talked to him later and I said, well, what'd you find? Of course, worst case scenario is you find 7,000 tiles in a big pile at the bottom of that. That's not a good day. They found about a dozen or so. But they've got part numbers on them, so we went back and checked. Every one of them were tracked back to the vehicle. None of them were in what we would call critical areas, so that a re-entry would not be an issue for the vehicle on its return. But it also indicated we're not done yet. We've got to go figure out and do a forensic analysis on each one of those, find out why it fell off, what was the failure mode, and so forth. To give you an idea of the challenges of the dynamics of this launch, here's a quick video that will give you, you've got all of this, you've got to move it, you've got to roll it out from the OPF over to the VAB, you've got to stack it, then you've got to put it on a transporter, you've got to move it down over to the launch pad, you've got to hook up everything that's got to be hooked up to it, you've got crews around it, and of course, don't bump any of those eggs. And then you have this tremendous vibration of the launch. Matter of fact, another subject is one we call the orbiter twang. If you've ever been and watched the IMAX down in California Science Center on the launch, if you watch very carefully on launch, we actually have a hold-down device that holds the orbiter when the solid rocket boosters and the engines fire. Holds it and keeps it, and then those release. Well, those hold-downs, when those engines fire, what we call the stack has a unique condition where you rev it up, and just like you've seen at the drag strips, when you rev the car up, it rises up a little bit. The orbiter stack would twang 4 feet in the launch position. One of the first things we had to do was redesign the platforms and make sure none of them were in the wrong place. As you saw, until that orbiter was on orbit, there were so many opportunities for failure, damage to the system, a very fragile system. But our launch, STS-1, AOK, our TPS, needed some tweaking, and two of the things that we had to do to increase the bond strength, we came up with a special formula to put on the back side of the tile, a densification material. We found that those tiles that had been failing, like the one who came off in the hand of the NASA guy, was because the density of the adhesive, which was RTV 566, by the way, when it was bonded, it wasn't strong enough. So when we densified, we increased the bond strength. The other thing that we found was in the orbiter conditions of Florida, it's a moist environment down there, seacoast, just like we have here, even more so. And because these tiles are porous, even though they have a glaze top coat, moisture could get into the tile. And when the moisture got in there, you run the risk of, as it would, if the moisture was retained in there and it heated too fast, it would turn to steam and it would blow out the face of the tile. So we had to waterproof the tile. Interesting little side story. We've got to waterproof. How are we going to waterproof the tile? So we're sitting around and George says, well, go get some Scotch Guard. He wasn't kidding. We sent a guy down to the local DIY shop, buy every can of Scotchgard you can get your hands on. We ran a quick lab test, and it worked. Oh, it looked terrible, but it worked. So the first flight that we did, we actually bought a tanker car of Scotchgard, and we Scotchgarded that whole darn vehicle. Of course, from then on, the instruction and orders came with a design change. All tiles being fabricated would have a special waterproofing agent at the time of manufacture put into it. So we didn't have to Scotchgard anymore, although it is the same formula. So, STS was very, very successful. It flew for several years until STS-107. Normally, I would do a separate presentation altogether on the failure of 107, but because we're talking about the TPS, and TPS played a role in the failure of 107 Columbia, I thought I'd just take a moment and go through that mode for you. But I want to remind everyone, STS-107 was one of the most successful flights of any orbiter. Over 110 experiments on that mission. 15 days in orbit. That crew and that vehicle did a marvelous job. But what happened? Well, what happened was, when the vehicle's on the launch pad, all the dynamics of what's going on, things are happening. And one of the things that we knew happened, the external tank was covered with a foam insulation that would come off periodically. There were some areas that it was loose, and it had at least 3 or 4 occasions where it came off. But it's foam. I mean, it was just styrofoam, very light, and not a problem. We didn't have a problem until we started investigating what happened on 107. On the top of the external tank, there's a feed pipe that goes through where the cryogenics go in. There's a foam cap. It's about the size of a carry-on bag you'd have on a airplane. And that foam cap came off. It came loose during vibration of the launch, and it came down. Orbiter going up, it impacted the leading edge of the wing, the RCC. Now, at first, everyone said, okay, we think we took a hit on the RCC. Well, we've had that kind of condition before, but it's no big deal. Well, we're not sure. We asked to see if we could get some cameras on it when it was in orbit to see if there was any damage in that area. That failed to happen. You can read the investigation report. There's many reasons, most of them not technical. But that didn't happen. So what did happen was, as the vehicle came back into the atmosphere at 225,000 feet, when the plasma reentry started, unbeknownst to the crew and mission control, there was a hole in the leading edge RCC. The first thing that the crew and the mission support saw was sensors in the wheel well for the landing gear said the tire pressure is increasing in the landing gear. Then the tire pressure was 0, was gone. Then the sensors started just lighting up the board like a Christmas tree. We lost comm. When we did the investigation, our suspicions were that more than what we thought happened with that foam impacting the RCC. So we did a test in the lab. Now let's go back to that styrofoam. If I just took a piece of styrofoam packing material you get out of any Amazon shipment you get, and I take it and I stand here and I throw it at you, what are you going to do? I'm probably going to maybe dodge it, but it's styrofoam. You know it's styrofoam, you're not going to worry about it. However, if I take that foam and I soak it in water, I put it in the freezer and I freeze it to where it's now frozen, and now I throw it at you, are you going to block it and duck? You better. When we did this lab test, what you're seeing in the lower right-hand corner of your screen is a simulated with actual flight RCC. We took and duplicated the conditions of that impact. We fired that foam block at that RCC. When we showed this picture to the NASA investigation team, they actually cried, and rightfully so. That took the lives of 7 beautiful pioneers and taught us a lesson, another one. The Space Shuttle program was 38 years. For 38 years, from 1962 to 2000, it was very productive. Yes. We had 32 missions, 2 failures. Comparing it to the Apollo in the spacecraft, the Apollo program was only 11 years, from 61 to 72. We learned a lot in building spaceships over the years. And Shuttle taught us so much and gave us so much. My hope is that the new generation of pioneers will remember and look forward, remembering the giants who contributed so much in these lessons learned, because tomorrow does not belong to us anymore. Our days, my days, they were beautiful, and I treasure and cherish every one of them. But the future belongs to the young. They're going to decide where we go, when we get there, and how. What I suggest to my audiences, and especially to the parents, and the family members, the grandparents, and the children, is keep dreaming, but keep the faith and have hope. And remember the mantra of that greatest generation: can do. And you can do it. Thank you. This is really my favorite part, the Q&A part. Over here. Well, the whole idea of the foam wasn't a problem until somebody got very creative in the early mission and said, you know what? We still need to lose weight. And they said, well, that external tank that we have out there, it's got a top coat of thermal protection paint. If we don't put that coating on there, we can save 400 pounds. So that was it. They eliminated the paint, the top coat on the external tank foam. It helped us save a lot of weight, not a lot of weight, it saved weight, but it opened up Pandora's box in terms of the moisture intrusion and others. I think in retrospect from the failure of 107, it's maybe Monday morning quarterbacking, but we had 3 other instances before it. And we should have said, look, we need to give this more serious consideration than we had. But that is a true statement. Yes? The question is, are the tiles interlocked? No, they are not. As a matter of fact, the other friendly term that we used to call the orbiter was the brickyard. Because when you would go up there when they were doing the early installations, you'd look at it and, hey, that's the patio in my backyard. No, they were just, there was a gap. There was a gap between all of the tiles. Now, there were 2 considerations on the gap from the design standpoint. The width of the gap was a problem because now you had heat intrusion that could pipe down and get down to the lower surface. But the other was because the tiles had a tendency to float because of the bonding and the strain pad, you had to avoid what we called a forward step. So if this tile is the aft tile and this is the forward tile and it's a little lower, then it puts a profile edge up, and now the aerodynamics create a lip. And the concern was another loving term we came up with, the zipper effect. The zipper effect was, well, I've got a tile that's a little bit higher in the back, aerodynamics coming in, it catches that edge, there's a gap between, and whoosh, that tile's gone. And if that one's gone, like an ear of corn, the next one, the next one, the next one. Well, the solution for both of those problems was another design material called the gap filler. And literally, it's just what it said. It was a piece of quartz fabric that was wrapped around a stiffener of some type, usually metal, and then it was all buttered up with RTV, and it was slipped down into the crack between the tiles. So when you were through, you had a contiguous surface across all of the tiles. And if you look at Endeavor over at the California Science Center, you can get fairly close enough to see some of those gap fillers that are still embedded in there. But then what happened was after every post-flight, we weren't looking for tiles, we were looking for gap fillers that fell out. Yes, there were gaps. Any other? Okay. Okay, the question is, from the bucket brigade, if we had found one of those tiles in a critical area, what would we have done? Well, immediately there was this Tiger team would have taken it and said, okay, where's it located? Question number 1 was always, if a tile comes off, it immediately exposes the surface of the vehicle, which is aluminum. Now, with the plasma heat on heat, we could calculate how long it would take for burn through. And of course, the burn through, if the heat was on the belly, it's going to be several thousand degrees. You'd have that plasma jet going through. So the next question is, what is behind that area where the burn through occurred? Is it empty space? Is it electronics? Is it the wheel well? So we were able, because of configuration management, we were able to tell exactly what the impact of that would have been. And we would have said, yay or nay, there's a problem or there isn't a problem. Now, the other part of your question, okay, we came up with some methods to fix that on orbit. We actually had a kit that the astronauts had on board every mission that they would have to go EVA, or depending on position, they could use the manipulator arm and go down, and they could actually, it's like a spray foam insulation, they could actually fill it, and it would give them a barrier that would bring them back in. Now, in the case of 107, had the scenario been, we've got a damaged leading edge, we have a crit 1. Crit 1 means a failure that would cause the loss of the lives or the vehicle. If it was a crit 1 failure, the options would have been rescue. We would have tried the repair first, and all I can say about that is, at least from our crew, the generations of Apollo, been there, done that. Apollo 13 was one of our proudest achievements. And so I would like to think we would have come up with a solution, but there were options. And we had another vehicle on the, at Kennedy that could have been turned around and launched to rescue that crew. But now, these are all, as the old saying goes, these are decisions above our pay level, and they were decisions that were either evaluated or addressed, and actually the most important one was the decision that, no, we're not going to turn our cameras over and look at it to determine whether or not there was a failure. Yes? Okay, the question is, how do they make these things? How do they make this tough? I need to find out if Lockheed ever documented the procedure, but it is pretty fascinating. First of all, you go find yourself a desert with the purest quartz sand you can. And believe me, that was a real challenge to start off with. And we paid dearly. As a matter of fact, if I recall, we ended up buying and stockpiling enough of it for every tile we could imagine we were going to be building. But you get this purest quartz as you can. Then you melt it, and it goes into this special machine. And then think of it as, and you've maybe seen this where a glass blower has liquid glass, and it's just a strand and a fiber, and it glows, okay? So you have a stream of that. Now, what happens if you take molten glass and you hit it with cold air? It explodes. As a matter of fact, it explodes in such a way that it produces these minutia fibers, little tiny fibers. And it's kind of like a plasma machine, and they create this, and they build this stuff up on a plate until it gets to a mass. And when it gets to a certain mass, then they take it off, and they cut it, strip it, and shape it. So now you have a pure quartz block. Then the next step is the firing of the glaze that they put on the outside. The glaze is there primarily to protect and hold, give it some integrity and structure, but also to prevent intrusion of water and moisture and that sort of thing. It's very significant to touch. That's one of the reasons I mentioned earlier. when you're installing it or handling these tiles, you had to wear gloves to make sure the oil of your skin would cause damage to the tile when they would fire it. Okay, the question is about the icing conditions during launch. It was more than just icing. It was the icing, and yes, there was concerns about ice formation because of the cryogens, because of the weather and whatnot. And essentially, you want a job? There was an ice crew. We had a crew. There was a crew down there. Their only job was to go knock these icicles off and make sure that they were cleared and kept away from the vehicle and the orbiter. Temperature was more the issue. As a matter of fact, it was that freezing temperature that was the problem of 51L. The reason we lost Challenger was because of that cold temperature. Not because of an icicle, but because the solid rocket booster is stacked in segments, and each one nests into the other one, and the joint is a double O-ring seal. Now, you're familiar with O-rings in pneumatic devices and that sort of thing, but imagine an O-ring seal. It's a double O-ring seal, and it's 20 feet in diameter. Now, stack that without rolling the seal out of the groove. That was just an incredible operation to watch, and it didn't always go well. We had some of the missions where the O-ring came out of the groove, and we would get then burned through. The propellant would actually burn through that joint section. It turned out on the 51L, I was in the office, and we had monitors around the engineering bays and whatnot, and I was on my way to a meeting with one of my engineers, and he said, "Oh, they're getting ready to launch. Let's go watch." Okay, let's go watch. So by that time, you know, it was getting pretty routine, but yeah, let's watch it. So we're watching it. As soon as that thing got off the pad, we knew immediately it was a failure. Just instantaneously, we knew that was not supposed to happen. So I had a folder in my hands, and I turned to my engineer, and I dropped it in a wastebasket. He said, "Aren't you going to your meeting?" I said, "No." He says, "What was the meeting about?" The meeting was about providing lists for staff reduction. We aren't going to be reducing any staff. We're going to go find out what the heck happened. Well, that same afternoon, this engineer came back into my office, and he drops a briefing on my desk. He says, "Here, look at this." And I flip it. I said, "What is it?" And he says, "It's a briefing. It's a briefing that I was at 3 months ago in October, before Challenger. It was a briefing describing the failure mode of the solid rocket booster seal because of cold temperatures during a launch cycle." They knew it. I mean, we knew the failure modes. You know, one of the other issues on complex problems like programs like this, when you think about the number of people involved, the number of systems involved, the engineering involved, you begin to realize that there are things that are going on that get lost in the shuffle. And part of the challenge is to, again, have everybody pulling that rope in the same direction, working as a team, so that if there is an anomaly or something that people need to know about, they do. And That's the lesson, one of the main lessons I'm hoping that the new generation is beginning to pick up on, that everything is important. Everything is important, especially when you're dealing with aviation and aerospace. People's lives are on the line. Thank you very much. I'll stay around if there's any other questions.